Okay, so we might as well start 1 minute earlier than the Berkeley time. It's a great pleasure to have Dave here with us to tell us a little bit about his work on what level PAs. I worked with Dave for what, 5 years now, I think. Yeah.
A long time.
Yeah, a long time.
Most of them were good years.
Yeah, exactly. He's a Harvard graduate, don't take that against him. But since then, he's been a professor at Carnegie Mellon and now North Carolina State University, and pretty much won every young investigator award you have around there, like NSF, PowerPoint White Paper, etc. He's been seen in Nature as well. So let's get it off.
All right, thank you. Thanks. So this is an overview. One of the things that Vladimir and I share is that we're interested in everything, and so I've done quite a bit in my my short career. Analog and RF circuits is sort of the main thrust. We had some very interesting projects. This is actually these little dots here are individual silicon atoms, and so we're looking at making nanoelectronic devices with AFM tips. So we did some of that. I did an NSF career award on spin torque oscillators, which is another nano electronic device. If you Google, you'll find out we did a football tracking work, and we've also built micro robots. So we've done quite a bit of stuff. But being here at Berkeley, I got to talk about circuits, and so I'm going to focus in on our PA work. So this is just a little bit of an outline. I'm basically going to talk about sort of the motivation for the work, and then also talk about single PAs, power combining, and I'll talk a little bit about the radio that we're trying to build. So the motivation for this work was an out-phase transmitter. If you're not familiar with it, the basic idea is you start with an amplitude and phase modulated signal that you want to send. You want to put it at an antenna, and the problem you have is that your power amplifiers don't like to operate except at maximum peak amplitude. They're very inefficient. So what you'd like to do is have both your power amplifiers operating at a phase-only modulated signal. And the way you can reconstruct your final signal is if you superpose these two, if they're in phase, you get twice amplitude. If they're out of phase, you get cancellation. So you can reconstruct that analog signal with the PA operating at a fixed amplitude. So we focused on amplifiers, and then also, while the out-phasing requires this combiner just to get the signals correct, it also allows us to focus on trying to get higher powers. So we did quite a bit of work on power combining, both for just getting the signals to sum, but also for higher output powers. When we started the work back in 2010, there was two metric areas. The first one was PAE, that's power added efficiency. We'll talk about that in a second. It was below 20% for almost all power amplifiers anywhere in the microwave regime. And we were looking at frequencies of 45 and 94 gigahertz. Those are both military bands. And here's a picture of where the state of the art was for output power. So for single PAs, these are stacked PAs, which I'll explain in a little bit. Everything was pretty much below 18 dBm. 17 dBm is 50 milliwatts, so pretty much 50, 60 milliwatts or below. And then everything was below, basically all the PAs were about 100 milliwatts and nothing above. So this is where we had started. You guys probably already know this, but I'm just going to do a quick review of the different classes of power amplifiers because it turns out in our work we moved between different classes depending upon the technology. So class A is simply we're just operating the transistor in a fully linear regime where we have a full swing on the collector here. And the power dissipated is just I times V. So whenever there's a crossover, we get some power. You run through the math. You end up with about 50% peak efficiency. Some people move into a class B, and this is where we bias it a little bit lower so that it's only on for half the cycle. We can use a filter to recover our sinusoidal here. But what we have here is the overlap in this region is 0, so we have no power dissipated. If you run through the math of how much the power and dissipation comes out, you end up with about 78% efficiency. The class B, as we know, is much more efficient. The class E has become popular mainly because processes have become faster, and it's much easier to really look at a MOSFET as a simple switch. If you're not familiar how class E works, I'm just going to go over the basic ideas of this. You basically have a load network that includes the drain capacitor. If you're not familiar, the big benefit of the Class E is you need a capacitor across the drain of the FET. The FET already has a capacitance, and so therefore you can reuse that as long as you have this capacitance is not too large. And we'll talk about the constraint on that. You've got a choke and some filtering that helps get the waveforms you want. I won't go in detail, but I want you to look over here, and these are the waveforms for the current and the drain voltage. And what you notice is it's not a simple sinusoid. We're doing some switching at some very particular times so that we can get the overlap that we want. And the key is we want to get that the voltage happens when the current is 0. And then when the current is positive, you want 0 voltage. If you put the product of those, you end up with 0 dissipation. And this all works if I had a perfect transistor. I could get 100% efficiency if this capacitance was below my design variable. Imagine I take my FET and just make it larger and larger and larger. I can make it so large that that drain capacitor does not meet this criteria, and I cannot get this, this ideal waveform. And I'll skip through the cartoon of how this all pulls together. A little bit too fast. So what happens when you actually put in a real FET? And so there's actually nice work a number of years ago on, if you just look at the on resistance and drain capacitance of a real FET, just take it off the simulation, can you calculate what the peak efficiency would be? And so we looked at a number of technologies from 180 nanometer CMOS to 45 nanometer, and it turns out at 45 gigahertz, which is one of our focus areas, the peak efficiency was 65%. So you go from 100 to 65 just by having a real transistor in there. So this was sort of, if you will, the maximum that you could ever get. So we've already dropped 35% here, but we're still well above that 20% that was a limit when the program had started. So I want to talk a little bit about output power. If you think about PA, if you want to make more output power, how do you do that? If you think about power as just being a product of I and V, it can increase I or it can increase V. There's several constraints for that. VDD is typically limited by breakdown voltage. You can cascode, but as we'll see later, cascoding gives you more power but reduces efficiency. Your most efficient configuration, just because the technology is today, is with a single cascode, but you can't go much above that. I could say that's fine. I'll keep my voltage and I'll just increase my current. How am I going to do that? I'm going to make a bigger device. As we talked before, if you get too big, the parasitic capacitance kills your ability to get an ideal waveform. The last piece, which is not so intuitive, is even if I fix my voltage and I increase my current as much as I can, the ideal load impedance for that PA reduces significantly. And it turns out that as this optimal Z out gets smaller and smaller and smaller, you're going to need large transformation ratios. And if you've looked at any of the theory for impedance transformers, the larger the ratio, the higher the loss. And it's sort of a nonlinear function. So if I got Z out down to an ohm, I'd burn maybe 20–30% of my efficiency just trying to convert that back up to 50 ohms. And so here's an example. On 45 nanometers, we could get Z out down to 5 ohms. And in simulation, you could do a quarter of a watt, which we never did achieve in silicon. But we'll talk about that in a second. All right. So I want to talk a little bit about power added efficiency, and this is not so much to educate you on how it is, but to show you just our design methodology. Power added efficiency is power out minus power in over power DC. And I can break that out into two pieces. One is the collector efficiency, P out over P DC, and the other one is my power gain. And then I can put these two back together and write PAE in terms of eta drain collector and gain. And so obviously, if I want to optimize this, I want my drain efficiency to be as high as possible, and I want as high gain as possible. And this is sort of how we do our optimizations for our power amplifiers. So we started looking at two processes. One was IBM 8HP, 130 nanometer SiGe, and then I'll show you a little bit later, we looked at the 45 nanometer SOI. And so the two components we had were collector efficiency and gain. And if we look at the different classes of PAs, it's not surprising Class E wins out with a higher efficiency, but Class B is not too bad. But if you go and look over in gain, this is where you really see that Class A, B, and Class B, they keep a high gain, but Class E doesn't. Class E has pretty poor gain. And that's mainly because in this process, we're looking at a bipolar transistor. And if you try to turn that on and off in a Class E, you're just dumping a ton of power into it. So the gain becomes pretty low. If you put that all in the equation, it turns out a Class B is actually optimal, even though theoretical architecture isn't the highest efficiency. So we set out to do a PA. We did a two-stage PA. And what we were going to do is look at optimizing collector efficiency and gain in two separate pieces. The first thing we did was do a Class A high gain pre-driver that maximizes A here. And then the second stage, we did a Class B high efficiency output here. So pretty much we did these in two separate steps. We didn't use a cascode here because we had dreams of doing supply modulation, and so we wanted to keep that cascode out. So we put all that together, and this is a look at the passives, so all of our biases. The big biases were done with spiral inductors, and the low value resonance were done with transmission line inductors. And here is a picture of the chip. You can see the bias inductors right here. We actually did a simulation of mutual coupling between them to make sure that that wasn't going to be an issue with coupled flux between them. This is just a cartoon of our test setup for all those of you that do measurements at millimeter wave frequencies. Even the adapters have a half a dB loss. So it was important to work through all of this in, you can see the cables, 6 dB of loss right there for testing. And so we got this back, and we went and took some measurements, and if you look on the left, the gain was pretty high throughout the input power range. The output power, it peaked at, let's see, 17.5 dBm, which is a little above 50 milliwatts. And also what was great was the PAE bumped up to 26%. So the previous works had all been below 20, so this was great at 26, soon to be outdone by UC San Diego. But this was really the first set of PAs out of our group, San Diego and Columbia, that really broke that 20% level. And this is just showing the power consumption of the different stages. And it's not surprising that most of the power comes from the output stage. So this was a record when we published it in 2012. This is just showing that as we change the supply voltage, the PA actually continues above 20% PAE. So it was ideal for using for supply modulation. Just kind of puts this in perspective. We popped up here on, like all curves, there's a state-of-the-art one that we popped up here at 45 gigahertz for PSAC. And the colors are by frequency. So if you want to look at colors, we're in this range. So here's the next one, and there's the next one. So those are the 2 points in this frequency range. So that was a great start for a single PA. We then went and looked at what we could do for CMOS. And we did the same analysis we did before. Not surprisingly, Class E is still higher for drain efficiency. But in CMOS, the Class E actually has pretty high gain. And that's because it's a lot less power to drive the gate. You go through the same optimization, and you end up with Class E as winning in a simulated environment. But there's one challenge when you're looking to build something other than just the PA. Most of the work that's out there, you'll see they show a little picture of the PA, and they show the measurement results for the PA. And they've actually taken a high quality, high power preamplifier and stuck it on the probe. So really they're measuring just the last stage or last 2 stages. Oftentimes they're putting in 10 dBm, 15 dBm into the PA to get the high output. If you want to, for instance, interface it with an on-chip radio, I don't believe your digital sections can output 10 dBm, particularly with multiple PAs. So one of the things we wanted to look at was how do we set up a PA that had a high gain pre-driver so that we could actually drive it from a digital stage and still get our high output. And this was obviously very attractive in CMOS because we could just use a series of inverters. It turns out it's not quite that easy, but that is the basic idea of where we started. And so the power stage was a Class E, almost exactly what I showed you before. We did use a cascode to get a little bit higher power, and of course we removed all of the inductors with transmission lines to increase efficiency. And one thing that if you're doing millimeter wave PAs you're probably familiar with, at lower frequencies they focus on the gate to source capacitance as being the main one that you want to resonate out. This interstage capacitance, so the capacitance between this gate and this drain, becomes an important capacitance that you need to resonate out. So really the trick to getting above 20% PAE has to do with this. So everybody who gets above 20% of millimeter waves is doing this, and Peter Aspect's group actually had a great, I don't know if it made it into the paper, but they actually had 4 chips they tested, and they were able to laser cut different tuning sections. And so they got up to 33% PAE on one chip. The other chips were 28. So these are 4 from the same run, they're laser trimming them, and they're able to get one just right. So the difference between 27, 28, and 33 is all how good you can do that. And so here's just a kind of a...
So what's the variation there?
The variation is, did you really model the capacitance at this node correctly? And the problem is that typically it's, with the interconnect, it's not modeled, and so your resonance here is not, you're not resonating fully out. The other problem that comes about as you move higher in frequencies, it's kind of funny because we always think about inductors as being lossy and capacitors as being great. As you move up in frequencies, the capacitors get worse and the inductors get better. So one of the problems with this is you have to put in a DC blocking capacitor, and you'll lose 3, 4, 5% in efficiency just from having that capacitor there. So this is a plot of the loss in the cascode stage. Without it, this is the time, so basically we're just walking through a cycle, and you can see with the tuner, you get rid of this big spike. And this is one of these games where you can reduce by 60% the normalized power in just M2. But I think the graph kind of shows all what you get. And so the question is, can I get this lower by doing a little better tuning? And if you can get higher efficiency. So this PA, we did an output match. This one had a 10 ohm and 2J. We built a load network to provide that, to optimize both our P out. And you can see efficiency and P out are optimized right around the same place. That was pretty lucky for us. And this is the power stage. So here's our full power stage with the pre-driver. I want to talk a little bit about this pre-driver, because as I said before, it's not just as simple of just putting some inverter stages together. So if you're an analog or RF person, you might think about a pre-driver as being some type of resonant amplifier. It's got high gain. The problem is they're usually big and bulky. If you're in a digital process, you think, why don't I just use an inverter chain? Very compact, wide beam. It turns out, though, that area can be a problem, but for this design it wasn't so much. But you lose your amplitude information. But if you run back to our whole goal here is to get a PA that runs a constant amplitude, so getting rid of the amplitude information isn't really a concern for us. And as you can see, at low frequencies you can put a nice square wave into your inverter chain. At 40 gigahertz you get a sine wave that's out. This is pretty typical, but that's not really the problem. The problem comes in with, we'll see on the next slide, I think we've got at least 15 inverters in a series. And if you stack a bunch of inverters in series, it turns out that the duty cycle, as you go through each one, will slowly either reduce or increase because the biasing gets affected as each one goes through. And what we found is if you did a balanced resistor to basically tie all these DC biases together, and you played with the value, you could actually get it where you maintain roughly the same duty cycle as you went through. And that was really important to get a decent duty cycle as we passed through. So here is the yellow is what we would get. And of course, being analog RF people, at the final stages, we said, why don't we throw in a few inductors to peak? Yes?
Sorry, so how do you ensure the biasing of the inverter itself? Because this is like a diode connected device, right? So, yeah, exactly. So here, like across process, the quiescent current is going to spread like crazy, right? Because it's kind of self-biasing. So if MO spreads, the bias will also spread.
Yes, but if you look at this as being ideally in just a single state, so one of these transistors is off.
Isn't it acting as an amplifier? Like, isn't it working?
It ideally should be acting as just an inverter, but as you point out at these frequencies, it is slowly, there is gain. If you go back here, you can see it's not giving you a digital output here. So what we did in simulation was play with these resistors till we got a duty cycle that didn't get disturbed. And you do consume more power, but our point was this was still better than doing a full RF pre-driver. We did put some peaking inductors at the end to basically just get a little extra gain at the end. And so this kind of shows the picture of, here we are, sizing of all the inverters. So these are just digital inverters getting larger, and then we have peaking inductors at the last stage. And this is how we implemented the balance resistors for that. And so here's the final PA. This is the P out. So we ended up with 18.7 dB of P out, so that's 75-ish milliwatts. 18% PA was not too bad. It's close to that 20. We'd like to get higher, but 18% is nothing, nothing to sneeze at. But we did achieve 30 dB of gain. And so now if, do we have a plot here of this? I don't believe we do. But at 18.7 dBm, you can see we can put in minus 10 dBm, and we can drive this no problem. So that, so this was pretty much the highest gain large output PA at the time that we published this. And we did remove the loss of this pre-driver just to see what this output would really be. And you end up with a raw PA of 29%. So all that came from this interstage matching that was done for this. So this really set us up to have a PA that we could then put on chip with a digital transmitter. And here you go. So you can see we saturate with as little as minus 12 dBm. So that worked out pretty nice. This is just a comparison of work. I'll just look at output power, 18.7, right in line with state-of-the-art from all the other groups. This is UCSD in Columbia. They're up 33, 34 compared to our 29. It's not too bad, but the gain, as you can see, the gain here is only 9.5 dB, whereas we have 30. So I think we did pretty good in achieving a realistic PA. We then took our PA designs and scaled them up in frequency. This is a two-stage 75 gigahertz. This is a standard Class E topology that we showed before. The key thing in these designs was figuring out how to lay out this interstage capacitance. So pretty much, if you're wondering what are people doing differently about millimeter wave at 45 and 90 gigahertz, we're really paying a heck of a lot more attention to what's happening right here. We still pay as much attention as everybody else did here, but this becomes more and more of a concern. And so here we are at PSAT at 17.2 dBm, it's 52 milliwatts, 20% drain efficiency. 11% PA is kind of low, but as you get up towards W bands, being in the teens is a good number. 60 gigahertz, people have done really well. They've gotten up to 20% PA at 60 gigahertz, but above that, drops off rapidly. So this had a pretty high power for the frequency range. And if you compared it to the other state-of-the-art, it had the highest power reported in that frequency range with a comparable PAE for the others. So that was a good work to move us up into a single PA. Up until now, we were just talking about single PAs, and we want to talk now a little bit about how we might go beyond that. But I'll just share one version of this that we did. We wanted to see about wide bandwidth. And so we actually designed the same architecture, but we, through a little bit of a luck and a little bit of dedication, we tuned the input and the output to be offset so that we get a wide bandwidth range. And this is simulation and measurement. We end up with I think it's a 67% fractional bandwidth, which as far as we can tell is the highest fractional bandwidth reported for a millimeter wave. Here you are, 36 gigahertz. At 15 dBm, 15.8 being peak power. So we were able to take that design and play with it a little bit to get the highest reported. This is just showing the fractional bandwidth. When we published this at 66.7. SCIRC, which is a year or two after our work just came out, and they published 51%. So for the PAs, single PAs, I think we did a pretty good job of kind of pushing the limits in all the directions for bandwidth gain and for high power PA. And so this is just a summary of our single PAs. Here we are for SIGI, and in CMOS, we've got state-of-the-art for both of these, and then obviously a wide bandwidth PA that pops in there. So that was a good starting point to start looking at power combining in higher output powers. So I want to talk a little bit about how we get higher power. And I'm going to walk you through a little bit of a cartoon analysis based upon all the data I'm going to show you is based upon actual design kits. So if you look at your power output, you can write it in terms of VDD squared over basically ZL. We talked about increasing VDD, we'll talk about that in a second, but you can also lower ZL. So as we said, we can lower ZL, that increases current, I get higher power, or I could just put a whole bunch of PAs in parallel to get higher power. And so we're going to look at how we do those and how the approaches compare for each one of those. So as I mentioned before, one thing you can do is increase VDD, right? And this was an idea that actually I think in the late 90s was introduced for stacking multiple FETs on top. I won't call them cascodes, I'll just call them stacked. And the idea here is to raise the voltage at this node. And the trick of why I don't call these cascodes is if I'm going to design M2 as a cascode, I'm going to get the gate as a fixed voltage, right? That's how I maximize the output impedance here and get high gain. In a stacked PA, I actually set up small capacitances on the gates and allow the parasitic capacitance from the drain nodes to feed in so that I get a sinusoid. And what I want to do is get the sinusoidal waveform on these nodes to be such that the gate to drain and gate to source voltage doesn't break down. So the idea is I'm sort of letting the voltage scale higher, but as long as all of the nodes don't exceed 1.2 volts differential each, I can go up to over 7 volts here in the CMOS process and not break down the devices. Now we are using an SOI process, which is what makes this possible. And the power combining is just increasing the voltage. If you will, I think one person called it series combining, if you will. And I like this picture because it shows you the, these are the VDS, these are the drain voltages, these are the absolute drain voltages, and you can see we peak up to 7.5 volts. And here is the drain to source voltage, and you see that if you look at it, we never get above 2.5 volts. And we're allowed 1.2 to 1.5 between gate and source and gate and drain, so 2.5 to 3 volts is our maximum. So this kind of tells you why this technique works so well, is you can get up to 7.5 volts without blowing up any one of your transistors. And here is the output power that we measured from this, and here's the power added efficiency. We were able to get 19.1 dBm at 19% PA, which was pretty decent. But if we look at this compared to other work, you can see that our power is very similar, PAE is very similar. What's different is it's kind of hard to see here. This is 0.09, everybody else is 0.16 or above. And the reason is when you stack these, your voltage gets higher, you have a higher output impedance. So when you do your load pull, your output impedance becomes a higher optimal value. And if you look at it, this is the 19 dB node, and if you move down just 1 dB of output power, this circle actually encompasses 50 ohms. So we can put a 50 ohm load on this stacked PA, and it's almost the optimal load. And when you do that, you don't need any output impedance matching network. And so without any output network, we're half the size of the smallest comparison to us with the same performance. So that allowed a little trick for us to get a high powered compact form, which would help for power combining. So let's continue with, instead of series, let's talk about parallel combining. And what we're going to do is I'm going to normalize everything to a VDD of 1. And then I'm going to look at, if I want to increase power, I basically decrease ZL. So on the plots, you'll see ZL getting smaller. That makes P out higher. And N is just the number of PAs. So we'll just do a quick example where I've got a single PA, and I'm just going to take ZL and make it really, really small. This is making the effect super big, lots of current to get higher power. And I just need to impedance match that from whatever that low value is up to 50 ohms. And in the parallel one, I'm going to parallel the PAs, and then I need some way to combine them. And the metrics I'm going to use is the efficiency of this box, insertion loss, and then also ZL, and I'm going to put it in here. So here's the efficiency of my box, and here is N, and I basically want to see how I can win. Obviously, if I put in a combiner that's 2% efficient, combining multiple PAs won't be a big help for me. And so if you look at taking ZL and making it super tiny to get more power, this is normalized power. So out here is more power. I'm reducing ZL to get out here. And here's the efficiency of this network. This was done in, I think, the SIGI 130 process. You can see I start out at over 90% efficiency, and I quickly decrease because of that impedance transformation ratio causes my loss to increase. You can then go look at another technique, a Wilkinson combiner, which we're familiar with. The Wilkinson combiner has a overall higher insertion loss because of the length of the multiple lines, but I can actually increase the number of PAs considerably. And here what I'm doing is I'm just increasing out to an 8-way Wilkinson, so I can get very high power. If you look at this, this is almost 5 times the power, but the insertion loss of this Wilkinson combiner is pretty significant. So I might want to look at a different approach to doing power combining, and one of the very popular ones is just using transformers, right? And the transformers are just basically paralleling all of these. If you look at the DAT architecture that was put out, that's basically a transformer combiner. And what you see is suddenly the transformer combiner has really high efficiency for these intermediate powers, so it's much better than the LC match, it's better than the Wilkinson, but it gets to be a problem when you want to get up to 8. If you've done power combining with transformers, just getting 2 or 4 together is a pain. Trying to get 8 or 16 is almost impractical. So it sort of stops at its maximum power just from the logistics of how do you get on a planar structure the power combining. And so what we looked at was maybe something that could bridge the gap here, be like a Wilkinson that would scale out, but then also have higher efficiency. And so what we focused on was something called a 0-degree combiner. And the 0-degree combiner is a combiner where we assume that all of the inputs are in phase. If you're familiar with a Wilkinson, the 2 inputs can be in phase, out of phase. Here we're looking at them all being in phase. And what's differentiating this from a Wilkinson is 2 things. The first is, right now you don't see any balance resistors, which you often see in a Wilkinson. And the other piece we'll see in a second is the length of these lines is well less than a quarter wavelength. In fact, from here to here, regardless of the number of PAs you combine, is a little bit over a quarter wavelength. Whereas a Wilkinson combiner would make this a quarter wavelength, that a quarter wavelength, and that a quarter wavelength. So let's take a little bit of a look into how we actually piece this together. I'm going to do a simple special case just so you can see how it works, and then we'll go into the actual combiner. So this is a special case where I'm doing a lambda over 4 combiner, and that's basically saying I'm constraining my total length to lambda over 4. And you're probably familiar, if I have 2 resistances, I can do an impedance transformation using quarter wavelength transformer and a Z0. Now just think for a second, what if I came in and magically just split a piece of this up into 2 pieces, and then a piece of this up into 4 pieces? So it's just like I went and I just split it into 4 parallel transmission lines, 2 parallel transmission lines. And I can split it arbitrarily wherever I want. You can see this is equivalent. These 2 would combine to be equivalent. If I had an ideal junction, these 2 would combine to be equivalent. And so this circuit is really just equivalent to this. The only thing is that the characteristic impedance has to scale so that the parallel combination is always Z0, right? And from here, it doesn't take very far to say, well, what if I just cut the line here and make these 4 different loads that are 4 times the impedance? And then you can say, aha, I now have my combiner, I just put in my PAs. And the length from here to here is a quarter wavelength, but it doesn't matter which individual lengths are, it's just the sum has to be a quarter wavelength. And so I'll do a quick design example. So we start with our load impedance, and the resistance we're going to put here is the target source impedance for the PA divided by the number of PAs we're combining. And this is just a quarter wavelength impedance transformation equation. And that'll tell me what Z0 is, and I can figure out what the characteristic impedance of each of these are just through, basically this is doubled and this is 4. keeping the length to a quarter wavelength. And I think I got an example here of 50 ohms. 6.25 ohms is my target. I calculate Z naught to be 17.68. I then want to go and figure out what these impedances are. 50 divided by 4 is 6.25, so that's where that came from. And I can calculate then what each one of my transmission lines are going to be. For those of you that have done on-chip transmission line design, two things should scare you. One is the high value here, but more importantly is the range. I can give you a 10 ohm microstrip transmission line, or I can give you a 150 ohm. What's really hard is to give you a 10 ohm and 150 on the same process. And really the constraint in this is this huge range of impedances that you need. You may think to yourself, all right, so this idea doesn't work. I just want to remind you, this is our toy example, where we assumed it was lambda over 4. And we sort of assumed this idea of paralleling. But we can actually do one constraint removal and actually fix this problem, which I'll show in just a second. So here's a millimeter wave implementation. This is a back-to-back 0-degree combiner. From here to here is about quarter wavelength. And here we are at 45 gigahertz simulation and measurement. So we have about 1.2 through loss of this. So this showed that we could actually build the variation in characteristic impedances and achieve a combiner with relatively low loss for these frequencies. One of the questions that comes up is, okay, that's great, but we liked the Wilkinson Combiner not because it was so long, but because it's odd mode. So that means when these signals are not in phase, it has perfect isolation. It turns out for the 0-degree combiner, if you were to make these interstage resistances complex, you could have perfect isolation just as you had with a Wilkinson. You just have to realize that looking into here is a complex impedance, and that's going to make these impedances need to be complex. So you could, in theory, do it, but in reality, it's very difficult to build a complex impedance reliably with the transmission line circuit. So we looked for, I'll call this an engineer's solution. How bad is it if we don't fix the odd mode problem? And so we went and did a simulation of a 8-way combiner. This is the simulated isolation with no balance resistors. And you can see there's a few ports that are below, have less than 10 dB of isolation, which is not too happy. So then my actually postdoc had the brilliant idea of what if I just put resistors here? They're real, not complex. And I only put them at these points and I ignore the interstage ones. So he's sort of saying I'm putting in something that might be better, but not ideal. And when you rerun the simulation, suddenly you see most of these numbers jump up to 20 dB of isolation, and we're at 12.6 as the minimum. So this is sort of a quick fix, is just to put a simple linear real resistor there, and that allows you to get enough isolation where your odd mode should be okay. And remember, we're driving all these PAs in phase, so the odd mode is just mismatch between the two. It's not like it's a large amount. So then I want to talk about this problem we had before. Before we had a toy problem of everything added up to lambda over 4. Well, what we realized quickly was that there's no reason why this length has to be lambda over 4. That toy problem is easy to understand, but what if I said these lengths can sum to something other than lambda over 4? And then I also said the characteristic impedances could be any value. And what this does is it allows you to modify the length of these and the characteristic impedance. You get that extra trade-off there. So I can basically make it longer to get a more realizable impedance. And so in this design, we're no longer requiring this to be twice of that. And so what we did is we actually took this circuit, and so we had the length of each one and the characteristic of each one as a parameter, and it turns out computationally it's a pretty simple problem to actually just sweep the lengths and the characteristic impedances over all possible values that you can build on your chip. So imagine I have 50 ohms here, I sweep them all, and they all give me a different impedance looking into this node. And the different combinations give me different losses. So what I do is I say, look, for every ZL that I get, go and look for the combination with the lowest loss, and I can plot that right here. So this is showing all the possible combinations, that give you the minimum loss at each ZL. And if you remember, the way we design our PAs is we do a load pull and it tells us where the optimal load is. So you can see there's an area with very low loss, and then on the edges we get very high loss. So now we've basically broken this. We can have any characteristic impedance, any length, and I just put in the values that I can achieve on chip. And so here's a design example. This is actually for 80 gigahertz. And we're going to start at 50 ohms. We're right here at A. And then these dashed lines are because of the parallel connection. So whatever transmission line is here and here, this is seeing half of that. So I basically have to, when I break out going here, I have to jump to this point, which is twice the impedance. And then the length takes me down here to B, and then because I have a split again, I go to twice the impedance, and then B brings me down to here, and then I split again for twice the impedance, and this is how I get up here. And that previous plot basically shows me how I got there, and this is the final layout. And so let's look at a couple of PAs that we did. This was probably our biggest work. This was a 16-way PA. You can see here's the 0-degree combiner in the center. This may look familiar. This is our single PA we saw before. You can see the 4 coils here. The extra 2 are just from a preamp because we need more gain. We can't shove 10 dBm into each one of these from the input here. And so it is basically the same stage we had before as a single PA with a pre-driver, just to give it a little extra gain. And here I think really is the picture that to me shows the big difference between the 0-degree and the Wilkinson. This is the layout of the two. So this is almost apples to apples comparison. This was a layout done in the process and simulated. It's almost 3 times as large, the Wilkinson is, and you can see the loss here is we have 89% efficiency and 65% efficiency here. So if you look at the picture, you can see the power of the 0-degree over the Wilkinson. And what do we lose? We lose some odd mode isolation, but that's about it. So here's the measurement results. Here's simulated and measurement of the small parameters. Here is the large parameters, and we achieved 28.4 dBm, which is 0.7 watts at 42 gigahertz. 10% PAE is not too bad for having 0.7 watts. Before this, PAs above 10 gigahertz were all just 100 milliwatts. So this was a significant improvement. If you look at this compared to other silicon germanium chips, there was a 3.5 times improvement. The other thing that I think is impressive about this is this technology had been around. I did my PhD with this technology. It's been around for over 10 years. So it's not like we just got in the latest technology and that's how we did this. The 0-degree combiner really is what popped us up to here. We were in a DARPA program with some other groups that did some great work, and the best that we would achieve at CMOS was here. So we're still 2.5 improvement over that. We then scaled it. We said, let's go to higher frequencies up into W band. So we took our CMOS PA topology and we did a Wilkinson combiner together for this. And here we were able to achieve 21 dBm. That's a little bit over 100 milliwatts, 5.2% PAE. PAE is kind of low, but once again, when you start getting a W band, up until recently, 4 or 5% was considered a good number. This was best in class. I think I showed here best in class for CMOS. UCSD actually did. They were able to do work. They published work out at IMS here. We both had the same papers. They used though the next generation process, and so they sort of got a big bump from technology, whereas we got a big bump from the 0-degree combiner that we used. So I want to talk a little bit about outphasing, and I want to talk about the next section is sort of a little bit of work in progress. And this is actually what we've been working with Vladimir on, and hopefully he'll give us some guidance after the talk. So I talked before about wanting to drive these two PAs with a constant amplitude phase variation signal. And so what I have to do is take my input and somehow generate 2 signals, S1 and S2, that are constant amplitude and phase variation, and have their summation give me whatever it is, the constellation that I want to do. Now, all along I've been talking about this power combiner as not being a Wilkinson combiner, right? But, I'm sorry, but when I talked about the outphasing architecture, I said, well, I want these to superpose nicely, right? So I told you I built something that when they're out of phase is not very ideal, but what I like in my transmitter is for them to add and subtract in an ideal way. And if you look back at this picture, A, the length of this, if you could think about it, this is one combiner coming together. So here is the summing junction. It's well less than lambda over 4. So we don't have any kind of nice, neat, theoretically clean combination of these two halves. So the question is, if I started modulating this half or that half out of phase, so heavy odd mode, what's going to happen? And we did an experiment where we just slowly changed the phase between the two halves, between 0 and 180. And the yellow is the measured, and the dashed is the ideal. And the majority of the slip we see here, we believe, is because even though these are phase locked over time, they slowly drift. They're phase locked with a 10 megahertz signal, and so you don't have the fidelity to keep 80 gigahertz exactly in phase. So this is static, so this tells us that even though this power combiner isn't tailored or designed for an odd mode, it at least does a static combination and summation in a decent way. And what we're now trying to do is trying to figure out how we can set this up to do outphasing and measure at the millimeter waves. There's a lot of challenges with the outphasing architecture. One of them is we have this constant amplitude signal that we're phase modulating. The bandwidth is not limited. It's a very wide bandwidth signal. Also, I'll show you a picture here, but the phase resolution of S1 and S2, these signals we're putting in that are constant amplitude, gets very high. With all millimeter wave, there aren't standard tests set up, so we're building our own. And I'll actually show you a little bit of this in the next couple slides. So this is an overview of what we've been trying to build up to. We've been doing our DSP in MATLAB. We load up all of our data into signal generators. And then this is the part you have to do. You've got to do a full up conversion from a 5 gigahertz carrier to 80 gigahertz. We then feed each of our two PAs. And then we take an output and down conversion and do a time domain and also a frequency domain. And here's our chip. I wanted to show this a little bit closer. This is a brass casing, and we've milled out a pocket for the IC to go in. And then also these are thin film decoupling capacitors. And this is the DC biasing that's coming up from boards underneath. So you bond wire this biasing to here, and then you can bind from here right to the chip. And then you can come in and probe with your RF here. This does a number of things. One, it makes it very fixed, so all your biasing is very robust. If you hadn't looked, 10% PAE at 0.7 watts puts out around 6 watts of DC power. So you need a nice heatsink in this. And now getting into a little bit of the DSP, there's not really new results here. I just kind of want to walk you through some of the challenges we're having in building the test setup. Ideally, this is the amplitude of the two outphasing signals, and this is the phase of the two outphasing. So if I want to do 16 QAM, I've got 4 levels of phase. The red and the blue are the amplitudes. Because they're the same, they stay constant. And here is actually the summation of the two. So basically, the output of our power combiner. And you can see a QAM constellation here. You can see the spectrum is very wide. And if you notice these little dots for the phase, this is representing the phase that we have to change here. They're pretty close to one another, so you need really high phase resolution to get the differentiation between these two. Nobody would ever do this. We put on some filtering to this, just like we do with any system. And if you add some filtering, I guess I don't show this here, you can improve this bandwidth. But because the bandwidth is so large, what most people do is they say, well, why don't we modulate the amplitude a little bit? Don't make it perfectly fat, modulate a little bit. And you can use a minimum shift key method to add a little bit of amplitude modulation. It reduces the phase shifts, and you get a more limited bandwidth. You notice before, we just kind of, well, I can just go here. We just went down to basically minus 30 dB and just kept on going out. And here we have something that dives off pretty quicker. and you get a nice pretty constellation here. So this is better, but we now have back and amplitude modulation. So we're trying to fix the wide bandwidth here. And one of the things we've been working on recently is an algorithm that keeps the two perfectly constant, but does a little bit of trickery in how we generate the phase, and we're actually able to get a nice clean limited bandwidth signal out of this. And so this is all basically setting up at 80 gigahertz to be able to drive these PAs in an outphasing architecture. So we built a W-band test setup to prove out all of the radio, if you will. And so we've got our signal generators, our up conversions. Here we're using off-the-shelf PAs. We're using a Magic T as our power combiner and down converting. This is a little bit of a close-up. So here is, actually here's our PA that we split. And then here's our mixers for the modulation. What we're going to do is take these two signals now, and we would replace the PA right in the center here, and then do our down conversion. This is a time domain of the output. This is the amplitude. This really is a constant amplitude. The variation you see here is because this is on a 2 millivolt scale. There's a lot of amplitude noise in the measurement. Here is the summation of the two. And if you go take a look at the picture, you find that S1 and S2 have this bandwidth, and the summation has basically the same bandwidth. So we're able basically to show we can up convert to 80 gigahertz, we can down convert, we can generate a nice band limited signal for this. And this was actually set up yesterday. This is taking that same setup and setting it up for the probe station. This is the brass block that the die's on. We're up converting. The components look different because this is at Q band. The other one I just showed was at W band. And we're testing today. So I'll leave you with the hope there. But I'm hoping that what we will find is that the superposition in the 0-degree combiner isn't a real significant problem. Because if it isn't, that would be a big win for power combining, because we get a lot higher efficiency, much compact size. And so we'll see from there. And this is sort of a summary of what I covered. I mainly just presented some of our single PA work, and then our power combining. The key to our power combining was the 0-degree combiner. For the single PAs, I'd have to say that really it's just good engineering, optimizing for the right technology, making sure we resonate at the parasitic capacitance of that interstage node. And what are we doing next? Well, we and the rest of the world just want to go higher in frequency, because that's what everybody in millimeter wave does. So, all right, thanks.
Okay.